Molecule. A molecule is a
Chapter
neutral...
6, Section 2, Covalent Bonding and Molecular Compounds. After this video, I want you to be able to define molecule and molecular formula. I want you to be able to explain the relationships between potential energy, distance between approaching atoms, bond length, and bond energy. Many chemical compounds, including most of the chemicals that are in living things and are produced by living things, are composed of molecules. A molecule is a neutral group of atoms that are held together by covalent bonds. A single molecule of a chemical compound is an individual unit capable of existing on its own. It may consist of two or more of the same type of atoms as in oxygen, or of two or more different atoms as in water or sugar. A chemical compound is a compound whose simplest units are molecules. These are called molecular compounds.
Group of atoms held together by covalent bonds. Water, oxygen, and sucrose or table sugar are examples of molecules.
The composition of a compound is given by its chemical formula. A chemical formula indicates the relative number of atoms of each kind in a chemical compound by using atomic symbols and numerical subscripts. The chemical formula of a molecular compound is referred to as its molecular formula. A molecular formula shows the types and numbers of atoms combined in a single molecule of a molecular compound. The molecular formula for water, for example, is H2O, which reflects the fact that a single water molecule consists of one oxygen atom joined by separate covalent bonds to two hydrogen atoms. A molecule of oxygen, O2, is an example of a diatomic molecule. A diatomic molecule is a molecule containing only two atoms. Formation of a covalent bond. As you read in section 6.1, nature favors chemical bonding because most atoms are at a lower potential energy when bonded to other atoms than they are as independent particles. In the case of a covalent bond and covalent bond formation, this idea is illustrated by a simple example, the formation of a hydrogen-hydrogen bond. Picture two isolated hydrogen atoms separated by a distance large enough to prevent them from influencing each other. At this distance, the overall potential energy of the atoms is arbitrarily set at 0, as is shown in Part A of Figure 6-5 on page 165 of your text or on the screen now. Now consider what happens if the hydrogen atoms approach each other. Each atom has a nucleus containing a single positively charged proton. The nucleus of each atom is surrounded by a negatively charged electron in a spherical 1s orbital. As the atoms near each other, their charged particles begin to interact, as is shown in 6.6 on page 165 or on the screen now. The approaching nuclei and electrons are attracted to each other, which corresponds to a decrease in the total potential energy of the atoms. At the same time, the two nuclei repel each other, and the two electrons repel each other, which results in an increase in potential energy. The relative strength of attraction and repulsion between the charged particles depends on the distance separating the atoms. When the atoms first see each other, the electron-proton attraction is stronger than the electron-electron and proton-proton repulsions. Thus, the atoms are drawn to each other and their potential energy is lowered, as is shown in Part B of Figure 6.5 on the screen now. The attractive forces continue to dominate and the total potential energy continues to decrease until eventually a distance is reached at which the repulsion between the like charges equals the attraction of the opposite charges. This is shown in Part C of Figure 6.5. At this point, which is represented by the bottom of the valley in the curve, potential energy is at its minimum and a stable hydrogen molecule forms. A closer approach to the atoms as shown in part D of figure 6.5, results in a sharp rise in potential energy as repulsion becomes increasingly greater than attraction. In figure 6.5, the bottom of the valley in the curve represents the balance between the attraction and repulsion in a stable covalent bond. At this point, the electrons of each hydrogen atom of the hydrogen molecule are shared by the nuclei. As shown in figure 6.7 on page 167 of your text or on the screen now, the molecule's electrons can be pictured as occupying overlapping orbitals, moving about freely in either orbital. The bonded atoms vibrate a little, but as long as their potential energy remains close to the minimum, they are covalently bonded together. The distance between two bonded atoms at their minimum potential energy, that is to say, the average distance between two bonded atoms, is called the bond length. The bond length of a hydrogen-hydrogen bond is 75 picometers. In forming a covalent bond, the hydrogen atoms release energy as they change from isolated atoms to parts of a molecule. The amount of energy released equals the difference between the potential energy at the zero level, meaning the separated atoms, and that at the bottom of the valley, when the two atoms are bonded together, as shown in figure 6.5 or on the screen now. The same amount of energy must be added to separate those bonded atoms. Bond energy is the energy required to break a chemical bond and form neutral isolated atoms. Scientists usually report bond energies in kilojoules per mole, which indicates the energy required to break 1 mole of bonds in isolated molecules. For example, 436 kilojoules of energy is required to break the hydrogen-hydrogen bonds in 1 mole of hydrogen molecules to form 2 separated hydrogen atoms. The energy relationships described here for the formation of the hydrogen-hydrogen bond apply generally to all covalent bonds. However, bond lengths and bond energies vary with the types of atoms that have combined. Even the energy of a bond between the same two types of atoms varies somewhat, depending on what other bonds the atoms have formed. These facts should be considered in examining the data on in table 6.1 on page 168 of your text or on the screen now. The first 3 columns in the table list bonds, bond lengths, and bond energies of the atoms in separate diatomic molecules. The last 3 columns give average values of specified bonds in many different compounds.
Chemical bonds form when reacting atoms reach a lower potential energy when bonded than those same atoms would have as independent particles. In forming a covalent bond, electrons are shared and energy is released. The same amount of energy is needed to break them apart. This is called the bond energy. Bond energy varies with different kinds of atoms, as shown in this table.
In summary, a bond forms when atoms are a certain distance from each other. At this distance, the atoms are in a low energy state. If they are closer together or farther apart, they will be in an unstable situation. All individual hydrogen atoms contain a single unpaired electron in the 1s atomic orbital. When 2 hydrogen atoms form a molecule, they share electrons in a covalent bond, as illustrated in figure 6.8 on page 168 of your text or on the screen now. Sharing electrons allows each atom in the hydrogen molecule to experience the effect of a stable electron configuration, in this case of helium 1s2. This tendency for atoms to achieve noble gas configurations through covalent bonding extends beyond the simple case of a hydrogen molecule. At this point, I hope that you can define molecule and molecular formula and explain the relationships among potential energy, distance between approaching atoms, bond length, and bond energy.